Hello my friends and welcome to my channel. This is Walter here, and today I'll be taking you through the October-November 2021 paper, that's 9231/11. I hope you're gonna learn a lot from this, so let's get started. Question number 1. It is given that alpha plus beta plus gamma is equal to 3, alpha squared plus beta squared plus gamma squared is equal to 5, and alpha cubed plus beta cubed plus gamma cubed equal to 6. The cubic equation x cubed plus bx squared plus cx plus d is equal to 0 has roots alpha, beta, gamma. Find the values of b, c, and d. Okay, so here we are going to consider first of all the fact that for this cubic equation, the sum of roots is going to be given by minus b over a. So in this case, that's minus b. And in our case, we've been given that the sum of roots, that's alpha plus beta plus gamma, is 3. So we can say minus b is equal to 3, which therefore means that b will come out as minus 3. So that's the value of b right here. Now, we've also been given here that alpha squared plus beta squared plus gamma squared is equal to 5. Now, we know that the sum of roots of the form alpha squared, which is alpha squared plus beta squared plus gamma squared, can be expressed as the sum of roots squared minus 2 of the sum of product of pairs. So here we have the information that the sum of roots of the form alpha squared is 5, and here the sum of roots squared is going to be 3 squared, and that's minus 2 of the sum of product of pairs. So therefore the sum of product of pairs should come out as 5 minus 3 squared, and that's all over minus 2. So that's equal to 5 squared minus 9, that's minus 4, and minus 4 over minus 2 gives us 2. Now the sum of product of pairs is represented by c in this case, so therefore we can say c comes out as 2. So we now have the value of c here. Lastly, we want to find the value of d, and to get the value of d, we are going to get the recurrence relation for this cubic equation. So here we have x cubed plus bx squared plus cx plus d equal to 0. Now we can make x cubed the subject, and here we'll be having x cubed is equal to minus bx squared minus cx minus d. So we get the sum of roots of the form alpha cubed being equal to minus b of the sum of roots of the form alpha squared and minus c of the sum of roots, and that's minus 3d. Now from the information given for the sum of roots of the form alpha cubed, we already have that as 6, and that's minus b. For b, we've gotten it as minus 3, so that's going to be minus of minus 3, so it will just be 3, and that's of sum of roots of the form alpha squared is actually 5, and minus c. For c we got 2, so that's 2 of the sum of roots, and the sum of roots we have it as 3, so it's 2 of 3, and it's minus 3d. So we can actually work out for d. So we'll be saying here that 6 is equal to 15 minus 6 minus 3d. So therefore we'll be having 3d being equal to 15 minus 6 minus 6, so that'll be 3. So therefore, we get D coming out as 1. So that's the value of D here. So we now have all the values we want. We got B to be minus 3 and C to be 2. So B is minus 3, C is equal to 2, and we got D to be equal to 1. So that's how we do it. Let's go on to the next question. Question number 2, Part A. Use standard results from the list of formulae MF19 to find the sum from r is equal to 1 up to n of terms of the form r of r plus 1 of r plus 2 in terms of n, fully factorizing your answer. Okay, so for this one here, we have the sum from r is equal to 1 up to n of terms of the form r of r plus 1 of r plus 2. Now, this is the same as the sum from r is equal to 1 up to n of r of, here we'll multiply r times r to get r squared, and r plus 2r, so that gives us 3r, and it's plus 1 times 2, and that's 2. So we can actually simplify this to the sum from r is equal to 1 up to n of r cubed plus 3r squared plus 2r. Using the distributive property, that's going to be the sum from r is equal to 1 up to n of terms of the form r cubed, and it's plus 3 of the sum from r is equal to 1 up to n of terms of the form r squared, and it's plus 2 of the sum from r is equal to 1 up to n of terms of the form r. So we can now use the standard results, and so I'll start from here for the sake of space. So here, for the sum to n of terms of the form r cubed, we have it as a quarter of n squared of n plus 1 squared, and that's plus, here we've got 3, and that's 3 of the sum from r is equal to 1 up to n of terms of the form r squared, that's a sixth of n plus 1 of 2n plus 1, and that's plus 2 of the sum of terms of the form r should be half of n plus 1. So we can actually simplify this. So here we've got a quarter of n squared of n plus 1 squared, and that's plus, multiplying 3 by a sixth, we get a half of n plus 1 of 2n plus 1, and that's plus, multiplying 2 by a half, here we get n of n plus 1. Now we can factorize, and I'm going to factor out a quarter of n plus 1. So if we do that, we will be having, dividing a quarter n of n plus 1 into this first term, we will get n of n plus 1 remaining. And it's plus, dividing a quarter into half of n plus 1 of 2n plus 1, we are going to get 2 of 2n plus 1 remaining. And it's plus, dividing a quarter of n plus 1 into this last term, we will only get 4. So this is what we have, and we can continue simplifying. So that's a quarter of n plus 1 of, inside the bracket we now have n squared plus n plus 4n plus 2 plus 4, and this simplifies to a quarter of n plus 1 of n squared plus 5n plus 6. And lastly, we can factorize this, so that's a quarter of n plus 1 of n plus 2 of n plus 3. So this here becomes the final answer. So that's it for part A. Let's go on to part B. On part B, the question goes, express 1 over r of r plus 1 of r plus 2 in partial fractions, and hence use the method of differences to find the sum from r is equal to 1 up to n of terms of the form 1 over r of r plus 1 of r plus 2. So here we're starting with 1 over r of r plus 1 of r plus 2, and we want to express it in partial fractions, of which it will come out as a over r plus b over r plus 1 plus c over r plus 2. So here we can make an identity that's 1 is equal to, and dividing r into the denominator, we get a of r plus 1 of r plus 2, and it's plus b of dividing r plus 1 into the denominator, we get r of r plus 2, and it's plus c, and dividing it into the denominator, we get r of r plus 1. So this is what we'll be having here. So now if r is equal to 0, then we'll be having 1 on the left side, and this 2 will be closed out, so we'll be having here 2a, which therefore will give us a as a half. And if r is equal to minus 1, we know that on the left side we still have a 1, and on the right side this terms will be closed out, so we'll be having here minus 1 times minus 1 plus 2, which is 1, so we get minus b here. So therefore we get b coming out as minus 1. And lastly, when r is equal to minus 2, here on the left side we still have a 1, and on the right side we cover up for this and this, so we'll be left with minus 2 times minus 2 plus 1, which gives us 2c. So therefore c comes out as a half. So now we can say this is equal to a over r. We got a as a half, so that's 1 over 2r, and it's plus b. b is minus 1, so it will just be 1 over r plus 1, and that's plus c. c is a half, so that will be plus 1 over 2 of r plus 2. So this is what we'll be having in partial fractions. Now the other part of the question goes, hence use the method of differences to find the sum from r is equal to 1 up to n of terms of the form 1 over r of r plus 1 of r plus 2. So we want to use the method of differences here. So let's put this here. So we're saying this should be equal to the sum from r is equal to 1 up to n of terms of the form 1 over 2r minus 1 over r plus 1, and it's plus 1 over 2 of r plus 2. Alright, so here when r is equal to 1, we'll be having a half minus 1 over 1 plus 1, that's 2, and it's plus 1 over 2 of 3, which is 6. And that's going to be plus, when r has a value of 2, we'll be having here 1 over 4, and that's minus 1 over 2 plus 1, which is 3, and it's plus 1 over 2 of 2 plus 2, which gives us 1 over 8. So we continue with the series. Next, when r has a value of 3, we'll be having plus 1 over 2r, that's 2 of 3, so that's a sixth, and it's minus 1 over 3 plus 1, that's 4, and it's plus 1 over 2 of 3 plus 2, so that's 1 over 10. I'll have another term, that's when r is equal to 4, so that we can establish a clear pattern here. So that's going to be plus and here it's going to be 1 over 2 of 4, so that's 1 over 8, and minus 1 over r plus 1 is going to be minus 1 over 4 plus 1, so minus 1 over 5, and it's plus 1 over 2 of 4 plus 2, which will give us 1 over 12. So I think we are good. So we also need the second from last term, so that's when r is equal to n minus 1. And for that, we will be saying when r has a value of n minus 1, substituting it, we'll be having 1 over 2 of n minus 1, and it's plus, substituting n minus 1 here, we get minus 1 over n, and substituting 1 over n here, we get 1 over 2 of n plus 1. And for the last term, that's when r is equal to n, we get 1 over 2n minus 1 over n plus 1 plus 1 over 2 of n plus 2. So these are the terms. So here, if you look at the terms, a half will add up to minus a half, and that will give us 0. A sixth minus a third plus a sixth add up to give us 0. An eighth minus a quarter plus an eighth add up to give us 0. So I think you can see the pattern. So here a tenth will add up to minus a fifth plus another term which is likely to be a tenth. That will be down along the line, and they'll add up to give us 0. And so this term will have something to cancel it out, and so will this term and this terms in the diagonal. So in the end, these terms will remain. What will remain is at the top a quarter, and we have 1 over 2 of n plus 1 and minus 1 over n plus 1 and 1 over 2 of n plus 2. Now this can simplify to a quarter. For 1 over 2 of n plus 1 minus 1 over n plus 1, we get minus 1 over 2 of n plus 1. And that's plus 1 over 2 of n plus 2. So this here is the final answer. Let's go on to part C. The question here goes, deduce the value of the sum to infinity of terms of the form 1 over r of r plus 1 of r plus 2. Now considering what we got for the sum to n right above, we can say that this is equal to the limit as n approaches infinity of, we got a quarter, minus 1 over 2 of n plus 1 plus 1 over 2 of n plus 2. And here we can say that for a quarter it's a constant, so we have it. Now here for the limit as n approaches infinity, this will tend towards 0. And here as n becomes large, this fraction will also tend towards 0. So we get the answer here as a quarter. So that's the answer to part C. Question number 3. The sequence of real numbers a sub 1, a sub 2, a sub 3 is such that a sub 1 is equal to 1 and a sub n plus 1 is equal to a sub n plus 1 over a sub n all to the power of 3. So on A, prove by mathematical induction that ln of a sub n is greater than or equal to 3 to the power of n minus 1 ln 2 for all integers of n that are greater than or equal to 2. And you may use the fact that ln of x plus 1 over x is greater than ln x for x is greater than 0. So here we're going to prove by mathematical induction, and we are going to start with our best case and consider that n is greater than or equal to 2. So we are saying let p sub n be the proposition that len of a sub n is greater than or equal to 3 to the power n minus 1 len 2. And first of all, we'll prove for the best case, that's when n is equal to 2. So p sub 2, and here for the left hand side, we'll be saying here that's len of a sub 2. And here a sub 2 is the same as using this a sub 1 plus 1 over a sub 1 to the power of 3. Now we've been given that a sub 1 is 1, so it's like we have len of 1 plus 1 over 1 to the power of 3, and this translates to len of 2 cubed, which is 3 len 2. So this is what we're getting for the left hand side. And for the right hand side, we have when n is equal to 2, that will be 3 to the power of 2 minus 1 len 2. And this simplifies to 3 len 2, which is equal to what we got on the left hand side. And so p sub 2 has been proven to be true. Let's go on to state the inductive hypothesis. So we'll be saying assume that the statement p sub k is going to be true. So therefore we can say len of a sub k is greater than or equal to 3 to the power of k minus 1 len 2. So that's the inductive hypothesis. So next, we are now going to prove the statement p sub k plus 1. Now this is going to be equal to len of a sub k plus 1, which in actual fact is equal to len of a sub k plus 1 over a sub k raised to the power of 3. Now this is the same as 3 len of a sub k plus 1 over a sub k. Now since we've been given that we can use the fact that len of x plus 1 over x is greater than len x, we can say that this should be greater than 3 len of a sub k. So in actual fact, we are saying that len of a sub k plus 1 has come out to be greater than 3 len of a sub k. Now from here, we can use the inductive hypothesis to say this should be greater than or equal to 3 to the power of k minus 1 len 2. And since 3 is 3 to the power 1, that's the same as 3 to the power of 1 plus k minus 1, which will just give us k. So it's 3 to the power k len 2. And I think you can now see here that technically 3 to the power of k len 2 is the same as 3 to the power of k plus 1 minus 1 len 2. And if we are going to put back the n, I'm sure you can see that it comes back to 3 to the power of n minus 1 len 2, which is actually what we want to get. So therefore, we can say that the statement p sub k plus 1 is true. That by the principle of mathematical induction, p sub n is also true for all integers of n greater than or equal to 2. So that's how we do it. Let's go on to the next part. That's part B. On part B, the question goes, show that len of a sub n plus 1 minus len a sub n is greater than 3 to the power n minus 1 of len 4 for n is greater than or equal to 2. So here we are going to say for len of a sub n plus 1 minus len of a sub n, this is the same as len of a sub n plus 1 over a sub n raised to the power of 3, and it's minus len of a sub n. Now this is the same as 3 len of a sub n plus 1 over a sub n minus ln of a sub n. Now we know that ln of x plus 1 over x should be greater than ln x. So what we've gotten here should also be greater than 3 ln of a sub n. And that's minus ln of a sub n. Now anything greater than 3 ln a sub n, if we subtract ln a sub n from it, should come out being greater than 2 ln a sub n. Now with this, we can now use this relationship to say that it's also greater than 2 times, and for ln a sub n, that's 3 to the power of n minus 1 ln 2. So that will come out being greater than 3 to the power of n minus 1 of 2 ln 2, which is 3 to the power of n minus 1 of ln to the power of 2 squared, which is ln 4. And that's what they want us to prove. And that's it for this question here. Question number 4. The matrix M is given by M is equal to the matrix with elements cos theta minus sin theta, and cos theta, pre-multiplying the matrix with elements 3, 0, and 0, 1. On A, the matrix M represents the sequence of 2 geometrical transformations. State the type of each transformation and make clear the order in which they are applied. So here we've got the 2 transformations represented by the matrices, and we will go in reverse order. So we start with the matrix 3, 0, 0, 1. Now for the matrix with elements 3, 0, 0, 1, if you consider a unit square, you will notice that the point 1, 0 has been mapped onto the point 3, 0, which is this point here. And the point 0, 1 is invariant under this transformation, so it's mapped onto itself. So you can actually see that this is a stretch by factor 3. So the first transformation is actually a stretch parallel to the x-axis with a factor of 3. Next, we go on to the second transformation, represented by a 2 by 2 matrix with elements cos theta minus sin theta, and cos theta. Now, this transformation represents a rotation, but to better understand what type of rotation it is, let's assign a value for theta. So I'll say let theta have a value of, say, 60 degrees. So if theta is equal to 60 degrees and I substitute it into this matrix, then I'm going to get the matrix with elements a half, minus root 3 over 2, root 3 over 2, and a half, which means that the point 1, 0 is mapped onto half and root 3 over 2, which is this point here. And the point 0, 1 has been mapped onto the point with elements minus root 3 over 2 and a half, which should be this point here. So the image will come out like this, and you can clearly see that it's a rotation about the origin, going in this case 60 degrees in an anti-clockwise direction. Now 60 degrees represents the angle theta, so we're going to say the second transformation is a rotation with a center at 0, 0 by theta degrees in an anti-clockwise direction. So that's the second transformation. Let's go on to part B. Find the values of theta for the range 0 to pi for which the transformation represented by M has exactly one invariant line through the origin, giving your answer in terms of pi. Alright, so we have right here the transformation M. So I'll just write that down. That's m is equal to, and we have cos theta minus sine theta, and we have sine theta and cos theta. Pre-multiplying the matrix 3, 0, 0, 1. Right, so we are going to multiply the two matrices. So row by column, we'll be having here cos theta times 3, which is 3 cos theta, plus minus sine theta times 0, which gives us 0. Next we go row and this column. So that's cos theta times 0, which is 0, and minus sine theta times 1, which is minus sine theta. Then lower row and first column, that's sine theta times 3, which is 3 sine theta, and it's plus cos theta times 0, which is 0. And lastly, we have sine theta times 0, which is 0, plus cos theta times 1, which gives us cos theta here. So this is the matrix M. So again, the question is saying, find the values of theta for which the transformation represented by M has exactly one invariant line through the origin. So the matrix M is an operator matrix. So I'll just write it down. That's 3 cos theta minus sine theta, 3 sine theta, cos theta. It is going to map the points x, y on the line and produce an image, which I want to call x dash and y dash. So that's the transformation that's going to happen. So here I'll simplify. I'll multiply the left hand side, where I'll be having this row times the column xy. We will be getting 3x cos theta minus y sine theta. In this row times the column, we will get 3x sine theta, and it's plus y cos theta, and it's equal to x dash y dash. Now, since we are talking about invariant lines through the origin, we know that the equation of the line is y is equal to mx. So we are saying since y is equal to mx, we can actually have two equations here. The first one being 3x cos theta minus y sine theta, but in place of y, I'm going to put mx. So it's as good as mx sine theta, and it's equal to x dash. Then for the second equation, I'll have 3x sine theta, and it's plus y cos theta. In place of y, we have mx again, so that's mx cos theta, and it's equal to y dash. So from here, we're going to say, since the lines are invariant, we can also say that the image will also have the form y is equal to mx. So that's y dash should be equal to m of x dash. So y dash is the 3x sine theta plus mx cos theta. So it has to be equal to m of x dash. X dash is the first equation. That's 3x cos theta minus mx sine theta. So let's simplify what we have right now. So we have 3x sine theta plus mx cos theta, and it's equal to, multiplying m into the bracket, we get 3mx cos theta minus m squared x sine theta. Now all the terms here are in terms of x, so we can actually divide all the terms by x, so that we'll be having 3 sine theta plus m cos theta is equal to 3m cos theta, and it's minus m squared sine theta. And I'll take everything on the right side to the left side, so that eventually we'll be having m squared sine of theta. And when we cross over 3m cos theta to the left, it will now be m minus 3m cos theta, which is minus 2m cos theta, and it's plus 3 sine theta, and that's equal to 0. So this is the equation that we end up having right here. Now, if you look at the question, we really want to find the value of theta for which the transformation has exactly one invariant line through the origin. So we're saying for one invariant line, this should mean that the discriminant, that's b squared minus 4ac, should be equal to 0. Okay, that's more like one real root. So here we can take this to be a quadratic equation where the coefficients are a is sine theta, b is minus 2 cos theta, and c is the 3 sine theta itself. So for b squared minus 4ac, we'll be having minus 2 cos theta squared minus 4 of sine theta and 3 sine theta, and that's equal to 0. So we can simplify this. So we'll be having here 4 cos squared theta minus 12 sine squared theta, and that's equal to 0. Now we can divide all the terms by 4 cos squared theta, and if we do that, then we'll be having here on the left side 1 minus 3 tan squared theta equal to 0, which gives us tan squared theta being equal to a third. And we can say that tan theta is equal to plus or minus 1 over root 3. Now, since according to the question, theta ranges between 0 and pi, the two possible value that theta will take should be 30 degrees and 150 degrees, which we can write in radian form as pi over 6 and 5 pi over 6. So these are the two answers as required. And that's how we do it. Question number 5. The plane pi has equation r is equal to minus 2i plus 3j plus 3k plus lambda of I plus k plus mu of 2i plus 3j. So on A, find a Cartesian equation of pi, giving your answer in the form ax plus by plus cz equal to d. Okay, so here we want to find the equation of a plane, and we know that from this form of the vector equation of a plane, we have been given a point on the plane and two direction vectors on the plane. So we can make use of the direction vectors to find the normal to the plane. So let's start with that. So for the normal to the plane, we do vector product with the direction vectors, starting with the first direction vector on the plane, which is 1, 0, 1, and the second direction vector, which is 2, 3, 0. So here we are going to get, closing out for I, it's 0 minus 3, so we get minus 3. Then closing out for j, that's 0 minus 2, so we get minus 2 from that, and factoring in the other minus, it becomes 2. Then here closing out for k, that's 3 minus 0, and we simply get 3. So what we now have is the normal to the plane. Now, the equation of the plane is going to be r dot and we'll be having the normal minus 3, 2, 3. And for D, we say A dot N, where A is a point on the plane. So we are going to take minus 2, 3, and 3. And it's dot N, which is minus 3, 2, 3. Now this simplifies to, for the dot product, we have 6 plus 9. And that gives us 21. So therefore, in Cartesian form, the equation of the plane, taking it from here, will be minus 3x plus 2y plus 3z equal to 21. So that's the answer to part A. Let's go on to part B. The line L passes through the point P with position vector 2i minus 3j plus 5k and is parallel to the vector k. Find the position vector of the point where L meets pi. Right, so here, the equation of the line L can be written as R is equal to A plus lambda B. A is a point on the plane, and we've gotten that to be the point 2, minus 3, and 5. So 2 minus 3, 5, and it's plus lambda of the direction vector of the line should be k, since the line is parallel to the vector k. So that's 0, 0, 1. So this is the vector equation of the line. Now I'm going to say let A be the point of intersection of the line L and the plane pi. So therefore, the position vector of OA should be equal to 2 minus 3 and 5 plus lambda, taking it from the equation of the line. And here you must know that lambda has its own specific value that is unique only to it. Now, since right above we got the equation of the plane as r dot minus 3, 2, 3 is equal to 21, that is r dot minus 3, 2, 3 is equal to 21. So therefore, the dot product of A, that is 2 minus 3 and 5 plus lambda, dot minus 3, 2, 3 should give us 21. So this means that minus 6 plus 3 or 5 plus lambda is equal to 21. That's minus 12 plus 15 plus 3 lambda equal to 21. So if we solve this equation for lambda, we will get lambda coming out as 6. So we now have the value of lambda, and therefore the position vector of A, that's OA, should be equal to, we're substituting now, 6 for lambda. So that will be 2 minus 3 and 5 plus 6, since it's 5 plus lambda. And this comes out as 2 minus 3 and 11. So that's the position vector of the point where L meets with pi. Let's go on to part C. On part C, the question goes, find the acute angle between L and pi. Now, to get the acute angle between the line and the plane, we will use this formula here, such that sine theta will be equal to the dot product of B, that's the direction vector of the line, and the direction vector of the line is 0, 0, 1. So that's 0, 0, 1 here. And N, which is the normal to the plane, which we got to be minus 3, 2, 3. So that's minus 3, 2, 3. And it's over the square root of 1 squared times the square root of minus 3 squared plus 2 squared plus 3 squared. So we can simplify this. For the dot product, we are going to get 3 at the top, and it's over the square root of 9 plus 4 plus 9. So that gives us root 22. So therefore, theta will come out as arcsine of 3 over root 22. And typing that in, we are going to get shift sine of 3 over root 22. And that gives us 39.8. So that's 39.8 degrees. And that's the value of theta here. Let's go on to part D. Find the perpendicular distance from P to pi. Right, so here we are going to use this formula here for the perpendicular distance from the point to the plane. Now remember, we have the equation of the plane as this. So let's paste it here. So that's the plane pi. And we also have the point P given. So therefore, we'll be saying D is equal to the modulus of minus 3 of 2 plus 2 of minus 3 plus 3 of 5 minus 21. And that's over the square root of minus 3 squared plus 2 squared plus 3 squared. So we can simplify this. So that's the modulus of minus 6 plus 15 minus 21. And that's over the square root of 9 plus 4 plus 9. So eventually we'll be having 18 over root of 22. So that's 18 divided by root 22, and to 3 significant figures we get 3.84. So the answer here is 3.84. So that's what we get for part D, and that's how we do it. Question number 6. The curve C has polar equation R is equal to 2 cos theta of 1 plus sine theta for values of theta ranging between 0 and a half pi. So on A, find the polar coordinates of the point on C that is furthest from the pole. So we are saying here, for the point furthest from the pole, dr by d theta should be equal to 0. So here we're going to look for dr by d theta, and we're going to use the product rule. So we'll be saying here 1 plus sine theta times the derivative of 2 cos theta, and it's plus 2 cos theta times the derivative with respect to theta of 1 plus sine theta. And we're saying this should be equal to 0. So this should give us, differentiating 2 cos theta, we get minus 2 sine theta. So that's minus 2 sine theta of 1 plus sine theta. And it's plus, here, differentiating 1 plus sine theta, we get cos theta. So we have 2 cos theta of cos theta. And that's equal to 0. So that's minus 2 sine theta minus 2 sine squared theta plus 2 cos squared theta, and it's equal to 0. So we can continue simplifying. So that's minus 2 sine theta minus 2 sine squared theta, and for cos squared theta, we use the identity that's 1 minus sine squared theta, and that's equal to 0. So we have minus 2 sine theta minus 2 sine squared theta plus 2 minus 2 sine squared theta equal to 0. So rearranging, we start with the 2, then the minus 2 sine theta, then for minus 2 sine squared theta minus 2 sine squared theta, we get minus 4 sine squared theta, and that's equal to 0, which is as good as dividing all the terms by 2. That's 1 minus sine theta minus 2 sine squared theta equal to 0. So from here we can actually factorize it, and if we do, we get a 1 here and a 1 here, minus 2 sine theta here, and it has to be plus sine theta. So we factorize it, and therefore we can say either the bracket 1 minus 2 sine theta equal to 0, such that we get sine theta being equal to a half, and then we can say or 1 plus sine theta is the one that's equal to 0, such that sine of theta will be equal to minus 1. Now, according to the question, theta ranges between 0 and a half pi. So we're only going to get a value between 0 and a half pi from sine theta being equal to a half. So theta is arcsine of a half, and that gives us 30 degrees, which in radians is a 1/6 pi. So that's the value of theta here. So now that we have the value of theta, we now want to find the value of r when theta is a 1/6 pi. So we can say here r is equal to 2 cos of theta. Theta is a 1/6 pi, so it's 2 cos of a 1/6 pi, and it's of 1 plus sine of a 1/6 pi. This is the same as 2 of cos of a 1/6 pi is √3 over 2, and it's of 1 plus sine of a 1/6 pi is a half. So basically we have 2 of √3 over 2 of 1 plus a half, which is 3 over 2. And we can simplify this. 2 and 2 cancel out, such that we are left with 3√3 over 2. So therefore, the coordinates of the point furthest from the pole are in the form r theta 3√3 over 2 and a 1/6 pi. So that's the answer right here. Let's go on to the next part. That's part B. On part B, the question goes, sketch C. Now to sketch C, we have to consider the polar plane. And here we can set up a table of values with values of theta between 0 and pi over 2. So I'm going to use a 1/6 pi increment. So here I'll be having 0, a 1/6 pi, a 1/3 pi, and a half pi. Now substituting 0 for theta into the equation, we get r coming out as 2. If we substitute a 1/6 pi for theta into the equation, we get r as 2.6. Substituting a 1/3 pi for theta, we get r coming out as 1.9. And substituting a half pi for theta into the equation, we get r coming out as 0. So we now have these points, and we can now plot them on this polar plane. So we start with 0, 2, which is this point here. Then a 1/6 pi and 2.6, which can be this point. Then a 1/3 pi and 1.9, which can be this point here. And lastly, half pi and 0. So we're back here at 0. So joining up the points, we get the polar curve coming out like this. So let's put it here. So this is the line theta is equal to 0, and we have the pole here. So the graph came out like this. That's the curve. Let's go on to part C. Find the area of the region bounded by C and the initial line, giving your answer in exact form. So here, to find the area bounded by a graph, we use this formula here. And in this case, we'll be saying A is equal to, factoring out a half, that will be a half of the integral from 0 to a half pi of 2 cos theta of 1 plus sine theta, and it's all squared, and it's with respect to theta. So let's integrate this. Here, I'll carry down the half, and the integral from 0 to a half pi, and squaring here, we'll be getting 4 cos squared theta, and expanding 1 plus sine theta squared, we get 1 plus 2 sine theta plus sine squared theta, and it's with respect to theta. Next up, we continue, and I'm going to factor out the 4. So the 4 comes in front, and we have the integral from 0 to a half pi, and I'll have the cos squared theta multiply into the bracket. So we'll be having cos squared theta plus 2 sine theta cos squared theta, and it's plus sine squared theta cos squared theta, and it's with respect to theta. Half of 4 is 2, and this times the integral from 0 to a half pi, and integrating cos squared theta, you have to consider this identity, which gives us a half of cos 2 theta plus 1, and it's plus, here we have 2 sine theta cos squared theta, just as it is, and for sine squared theta plus cos squared theta, we can find a way to express it in the form of sine 2 theta using the double angle identity formula. So sine squared theta cos squared theta is the same as a quarter of 4 sine squared theta cos squared theta, which is the same as a quarter of 2 sine theta cos theta squared, which is the same as a quarter of sine 2 theta or squared, or a quarter of sine squared 2 theta. So I'll write that as a quarter of sine squared 2 theta, and it's with respect to theta. Now here I'll put the 2 inside, so we'll be having the integral from 0 to a half pi of 2 times a half, that's 1, so we'll be having cos of 2 theta plus 1, and this plus, this becomes 4 of sine theta cos squared theta, and it's plus, this becomes a half of sine squared 2 theta, and it's with respect to theta. I'll be having the integral from 0 to a half pi of cos 2 theta plus 1 plus 4 sine theta cos squared theta, and for sine squared 2 theta, we can use this identity here, which means that we'll be having a half of 1 minus cos 2 of 2 theta, which is as good as a quarter of 1 minus cos 4 theta, which I can write as a quarter minus a quarter of cos 4 theta. So that's a quarter minus a quarter of cos 4 theta, and it's with respect to theta. So one more step before we integrate. So that's the integral from 0 to a half pi of, here we have 1 plus a quarter, which is 1 1/4 of 5/4, and it's plus cos 2 theta, and it's plus 4 sine theta cos squared theta, and it's minus a quarter of cos 4 theta with respect to theta. So we are now integrating 5/4, we get 5/4 of theta, and it's plus integrating cos 2 theta, we get a half of sine 2 theta, and integrating 4 sine theta of cos squared theta, we can consider that integrating sine x of cos to the n of x with respect to x gives us minus 1 over n of cos to the n plus 1 of x plus c. So in this case, we will get minus 4/3 of cos cubed of theta. And that's minus, here integrating a quarter of cos 4 theta, we get 1/16 of sine of 4 theta. And the limits are 0 and a half pi. So next we substitute a half pi into this. So if we do that, we'll be having 5/4 of a half pi, and it's plus a half of sine 2 theta. Sine 2 of a half pi is like sine pi, which is 0, and it's minus 4/3 of cos cubed of theta. Now cos of a half pi is 0, so again this is going to be 0, and it's minus 1/16 of sine of 4 of a half pi, which again is 0, so we have a 0 here. So we've substituted a half pi. Now we want to substitute 0, so it has to be minus for 0. Substituting it into 5/4 of theta, we get 0. Substituting it into half of sine 2 theta, we get 0. Substituting it into minus 4/3 of cos cubed theta. Now cos of 0 is 1. So here we'll be having minus 4/3 of 1, which is just minus 4/3. And it's minus here, minus 1/16 times sine of 0, we get 0. So here, for this first part, we'll only be having 5/4 of a half pi, which is 5/8 of pi. And here on the second, it's minus of minus 4/3, which is plus 4/3. So that's all we're left with. And this happens to be the answer. Question number 7. The curve C has equation y is equal to 4x plus 5 over 4 minus 4x squared. On A, find the equations of the asymptotes of C. So here we are going to start with the vertical asymptote. For the vertical asymptote, we are going to equate the denominator to 0. So that's 4 minus 4x squared equal to 0. Now this is the same as 4 of 1 minus x squared equal to 0. That's 4 of 1 plus x and 1 minus x equal to 0. So therefore, from here, equating 1 plus x and 1 minus x to 0, we can get x being equal to minus 1 and x being equal to 1 as the two equations of the asymptotes. Next, we look for the horizontal asymptote. For the horizontal asymptote, we can simply look for the limit as x approaches infinity of 4x plus 5 over 4 minus 4x squared. So this is the same as the limit as x approaches infinity of, and here I'll divide all the terms by the highest power of x in the denominator. So I'll divide all the terms by x squared. So 4x over x squared will give us 4 over x. 5 over x squared is just going to be 5 over x squared. 4 over x squared is 4 over x squared. And it's minus 4x squared over x squared. That will just be 4. So therefore, the limit here will come out as, here for 4 over x, as x approaches infinity, this tends towards 0. For 5 over x squared, this tends towards 0. For 4 over x squared, as x approaches infinity, this tends towards 0. And we have the constant here, minus 4. So it means that we'll be having here 0 over minus 4, which is 0. So therefore, we can say that the horizontal asymptote is y is equal to 0. Let's go on to part B. Find the coordinates of any stationary points on C. Right, so for the stationary points, we will say dy by dx is equal to 0. Now for dy by dx, we will use the quotient rule, and that will be 4 minus 4x squared times the derivative with respect to x of 4x plus 5. And it's minus 4x plus 5 times the derivative with respect to x of 4 minus 4x squared. And that's over 4 minus 4x squared all squared. And we're going to equate this all to 0. So therefore, after multiplying both sides by the denominator, we'll be having on the numerator here, simplifying it, that's 4 minus 4x squared. And that's off. Differentiating 4x plus 5, we get 4. And it's minus 4x plus 5. And differentiating 4 minus 4x squared, we get minus 8x. So that's equal to 0. So next, we will have 4 or 4 minus 4x squared. And it's plus 8x of 4x plus 5. And it's equal to 0. That's 16 minus 16x squared plus 32x squared plus 40x equal to 0. So rearranging, we'll be having 16 and plus 40x. And for minus 16x squared plus 32x squared, we get 16x squared. And that's equal to 0. Now dividing all the terms by 8 and rearranging, we'll be having eventually 2x squared plus 5x plus 2 equal to 0. So now we can factorize this. So we'll be having here 2x and x. And we'll be having here 1 and 2. So that's plus and plus. Which therefore means that either 2x plus 1 equal to 0 or x plus 2 is the one that's equal to 0, such that x is equal to minus a half. And here x comes out as minus 2. Now to get the corresponding y values, we have to substitute into the equation. So from the equation, y is equal to 4x plus 5 over 4 minus 4x squared. We'll start by substituting minus a half to get the corresponding value of y. So we are saying here minus a half, which is minus 0.5. And we are going to store that into x. So we are saying here we have y is equal to 4x plus 5, and it's over 4 minus 4 of x squared. So if x is equal to minus a half, we get y coming out as 1. So here we can say y is equal to 1. And when x is a value of minus 2, so we'll say here minus 2 and shift, and we store it into x. So substituting it into 4x plus 5 over 4 minus x squared, we get a quarter. So here, if x is equal to minus 2, y is equal to a quarter. So for the coordinates of the turning points, we'll be saying that's minus a half and 1. And we also have minus 2 and a quarter. So these are the two coordinates of the turning points. So that's it for this question. Let's go on to the next one. On part C, the question goes, sketch C, stating the coordinates of the intersections with the axis. So now to plot the curve, we'll have the axis, and we need to consider the following things. First of all, we are going to consider that we have asymptotes, and from part A, we got that the asymptotes are the lines x is equal to minus 1 and x is equal to 1. These are the vertical asymptotes, and the horizontal asymptote is the x-axis. Next, we'll need to consider the intercepts. So here, considering the equation of the graph, for the y-intercept, that's when x is equal to 0. And when x is equal to 0, y comes out as 5 over 4. So the y-intercept is the point 0 and 5 over 4, which can be this point here. For the x-intercept, that's when y is equal to 0. And when y is equal to 0, substituting it into the equation, we get that x comes out as minus 5 over 4. So the x-coordinate is minus 5 over 4 and 0, which is this point here. We should also consider that there are turning points to this graph, which we worked out in part B, and we got them to be minus a half and 1, which is this point, and minus 2 and a quarter, which is this point here. Next, we can consider the behavior of the graph about the vertical asymptotes. Let's start with the vertical asymptote, x is equal to 1. If we take a value that is slightly less than 1, say 0.999, substituting it into the equation, we will get y coming out as 1125, which is a very high value, which will be coming out from around here. And for a value that is slightly greater than 1, for that I can take the value for x as 1.001, and for such I'll get y coming out as minus 1125, which is a very small number, so it should be coming out from down here. I go to the next asymptote, that is x is equal to minus 1, and I'll take a value that is slightly less than minus 1, so I'll take the value minus 1.001. And if I substitute that into the equation, I get y coming out as minus 124, which is a small value, so it should be coming from down here. I'll take another value that is slightly greater than minus 1. Say here I'll take the value of x being minus 0.999. And for this value, if I substitute it into the equation, I get y coming out as 125.6. So it should be coming from somewhere at the top here. Now, it's also important for us to determine the behavior of the graph as x becomes very large or very small. So as x approaches positive infinity, I'll take a large value of x for that, say x equal to 1000, and substitute it into the equation of the graph. And when x is 1000, y is minus 0.001. So it should be coming from down here, just slightly below the x-axis. And as x becomes very small, that is as x approaches negative infinity, I'll take a value that is very small, like x is equal to minus 1000, substitute it into the equation, and I get that y comes out as 0.000999, which is slightly above the x-axis, so somewhere here. So I now have all the markers for my graph. So if I'm to join it up, I'll get the graph coming out this way. So this here is the graph. So here the graph will come out like this. And on this part, it will come out like this. And for this tail, it will be like this. Now the question also says stating the coordinates of the intersections with the axis. So we have two intersections with the axis. We have this point here and this one here. And by calculation, we got those points to be -5/4 and 0. And we also had 0 and 5/4. So this is the point -5/4. And this here is the point 5/4 on the y-axis. So this is what we have. Let's go on to part D. On part D, the question says, sketch the curve with the equation y is equal to mod of 4x plus 5 over 4 minus 4x squared, and find in exact form the set of values of x for which 4 of mod of 4x plus 5 is greater than 5 of mod of 4 minus 4x squared. So here we are going to start with the modulus graph. So I'm going to take this upper part of the graph and I'm going to paste it here. So we have here -5/4, and we have -1, and we have 0, and we have 1 here, and this is the x-axis, right? So we will reflect the part of the graph that is below the x-axis. So we start with this tail that goes down. So we'll reflect it above the x-axis. So it should come out like this. And next we will reflect this tail that is below the x-axis, above the x-axis. So it will come out here. So we have it like this. So this is how the graph will be like. So next we want to solve for this inequality. So let me paste it here. And it's the same as we have the modulus of 4x plus 5 over 4 minus 4x squared being greater than 5/4. So that's the same thing, which means we are looking for the interaction of the graph of modulus and the line y is equal to 5/4, which happens to be this line here. So we shall need to find the points of intersection for the two, which is this point, the point at 5/4 there, which is already there, and this point here. So we have 4 points of intersection that will help us determine the set of values. So here we are looking for when the graph of 4x plus 5 over 4 minus 4x squared intercepts the graph of y is equal to 5/4. So that basically is where the line y is equal to 5/4 intercepts this curve here. So that's for these 2 points of intersection. And we also want to find where the reflected part of the graph, which is the one in blue, which is minus of 4x plus 5 over 4 minus 4x squared, intercepts the same line, which is y is equal to 5/4. So here we're talking about these 2 points. So let's work that out. So we'll be having here cross multiplying 4 of 4x plus 5 is equal to 5 of 4 minus 4x squared. So that's 16x plus 20, and that's equal to 20 minus 20x squared. So that will give us here 20x squared plus 16x equal to 0, such that if we factor out 4x, we get 5x plus 4 being equal to 0. So here we'll get the values of x as 0 or minus 4/5. Let's also solve for the other one. Cross multiplying, we'll be having minus 4 of 4x plus 5, and that's equal to 5 of 4 minus 4x squared. So that's minus 16x minus 20 is equal to 20 minus 20x squared. So we can simplify this to get 20x squared minus 16x minus 40 equal to 0. Dividing both sides by 4, we get 5x squared minus 4x minus 10 equal to 0. So we can actually solve this quadratic using the calculator. And here we'll be saying for equation that's 5 and it's quadratic, option 3. So that's 5, the coefficients 5, then minus 4, then minus 10. And the values of x we get are 2 plus 3 root 6 over 5. So x is equal to 2 plus 3 root 6 over 5. And we also have x being equal to, and other value is 2 minus 3 root 6 over 5. So that's 2 minus 3 root 6 over 5. So we now have the values. So this value here is for x is equal to 2 minus 3 root 6 over 5. And this value here is the one for x is equal to minus 4/5 that we got. This one is when x is equal to 0. And this point here is when x is equal to 2 plus 3 root 6 over 5. So to solve this inequality, we're looking for the set of values for which the modulus graph is greater than the line y is equal to 5 over 4. In other words, where the modulus graph is above that of the line. So if you consider here, you notice that for values that are between 2 minus 3 root 6 over 5 and minus 4/5, the graph of modulus is above or greater than that of the line. So the first inequality here is from 2 minus 3 root 6 over 5 to minus 4/5. Going back, we can also see that for values that are between the point x equal to 0 and x is equal to 2 plus 3 root 6 over 5, the graph of modulus is also greater or above that of the line. So it's between these two values. So that's another inequality that's between 0 and 2 plus 3 root 6 over 5. So these are the two inequalities we get. And that's how we do it.